Thank you for the introduction. And I would like to thank the organizers for inviting me to this wonderful conference. And it's my great pleasure to give a talk here. And so let me start with a consequence of main theorem of this talk, not the main theorem itself. So let gamma be a countable group, and Y be a cat-zero space, which is locally compact or of finite telescopic dimension. And here, locally compact is the same as proper. And this notion, introduced by Caprese and Lichak, is already mentioned in Anders' talk. But so for the sake of simplicity, I concentrated to the case that Y is locally compact in this talk. But what I'm going to tell you is valid for this class of cat-zero spaces. And I will give you the definition of cat-zero space in a few minutes. And let this group gamma acts on Y be a homomorphism rho from gamma into the isometry group of Y. You have an isometric action of gamma on Y. And let mu be a irreducible symmetric probability measure on gamma with finite second moment. And here, so this is just a measure on countable set gamma. So it's a function on gamma, which is non-positive, non-negative, and the sum of all values is equal to 1. And irreducible means that the support of this mu generates this group gamma. And symmetric means that this takes a value, the same value at gamma and its inverse, gamma inverse. And so about this moment condition, I will explain you later. And so for any gamma and rho, you can always find mu satisfying this assumption. So this doesn't put any restriction to the action rho here. And the assumption on the action rho is here. So I assume that rho of gamma does not fix a point in the boundary at infinity of Y. I also give the definition of this later. And so this means something like this action given by rho is not so small in some sense. Under this assumption, we have two possibilities. The first one is this. So there is a flat subspace, which is invariant under the action given by rho. And here, flat subspace is a convex subset of Y, which is isometric to Euclidean space of some dimension. And dimension can be 0. And in that case, this means that this action, rho of gamma, fixes that point. And the other possibility is this. So there is a boundary map between the boundary of group gamma and boundary at the infinity of Y, and it's canonical. And here, boundary of gamma here is a Poisson boundary of gamma pair, gamma mu. And it can be viewed as a kind of boundary at the infinity of this group gamma by defined by a probabilistic way. And here, map is canonical means that, so this, I'm sorry. So this map comes from the orbit map. And so rho equivariant means that just this. So there is a natural action on this boundary of Y and Poisson boundary of gamma, and this map phi is compatible with the action of both space. And such a canonical equivariant boundary map is often very useful in rigidity theory. And sometimes so it implies very strong rigidity result, such as superrigidity theorem due to Margulis. But I have to say that so there was a very similar result due to Badel, Duchesne, and Lecroux. And they proved almost the same result, but so their construction of boundary map is kind of a very abstract one. And it's not clear that their map comes from the orbit map. So it's not clear that it is canonical or not. In this sense, this theorem is a refinement of their theorem. And so let's go back to the first case. So in this case, the action given by rho is rho reduced to that on flat subspace, that on Euclidean space. So in this case, the core of this action is on the Euclidean space. And Euclidean space is, of course, the simplest cat-zero space. So you may agree with me if you see the definition. And the action on Euclidean space must be the simplest one among all group actions on cat-zero space. So it says, under this assumption, either the action is very simple or we get a very useful tool. So this is a good news. And so this is a consequence of our main theorem, and which tells you something about the behavior of random walk transplanted to Y via orbit map. And I will explain it later. Is it okay so far? And so let me remind you some basic definitions. So I'll give you the definition of cat-zero space. So let Y be a complete metric space. And then geodesic, the map defined on an interval is called geodesic if it is isometric embedding. And space Y is a geodesic space if any pair of points can be joined by geodesic. This is already explained in Gerard's talk. And Y is cat-zero space if every geodesic triangle is thinner than Euclidean one. So it's just explained in this picture. So take any geodesic triangle in Y. Then the length of edges satisfy triangle inequality. So you can draw a triangle in Euclidean space which has the same edge length. And so there are isometric correspondence between these corresponding edges. So take any point Q1 and Q2 on edges on this triangle in Y. Then you can find a point corresponds to this Q1 and Q2 on the edges of this Euclidean triangle and compare the distance between them. And if the distance between Q1 and Q2 is less than or equal to distance between Q1 bar and Q2 bar, then we say, and this is true for any pair of points on edges on this triangle, then we say this triangle satisfies cat-zero condition. And if every geodesic triangle satisfies cat-zero condition, then we call geodesic space the cat-zero space. And so the simplest example is a simply connected Riemannian manifold with non-positive sectional curvature. So this follows from comparison theorem. And so other than manifold, trees and Euclidean buildings are cat-zero spaces. They have singularities, but they are very good cat-zero spaces. And And an important feature of cat0 space is the convexity of distance function, which means that for any pair of geodesics, C and C prime, the distance function, so the function which assigns t to the distance between C of t and C prime of t is a convex function. For example, so if you take C and C prime to be a geodesic giving these two edges of Euclidean triangle, then this is of course linear. And if you take C and C prime to be a geodesic giving these edges of the triangle in Y, then because this triangle is thinner than this one, this function should behave like this. And maybe it's easy to imagine. So this must be a convex function. And also comparison theorem in Riemannian geometry tells us that the strength of this convexity is related to the negativity of the curvature. And if the negativity of the curvature is strong, then for example, triangle in that space is very thin. And then, I'm sorry. Okay, I should say this also. And I'm sorry. So, and this convexity is true for any pair of geodesics. And also, we can change the speed of geodesic. And for example, if you take B to be 0, then this means that distance function from some fixed point is convex along geodesic. And let me go back to negativity. And, I'm sorry. Okay, it's okay. So, as I told you, so the strength of the convexity is related to the negativity of the curvature. And this is also explained in Jagal's talk, even in metric space case. But as long as we are dealing with cat0 space, we can expect the converse. So if the convexity of the distance function is the weakest one in some sense, then we can expect the set is flat. And it is true in some particular cases. For example, it is true for triangle. So if you have triangle, suppose you have triangle in cat0 space. And suppose that the distance function between two geodesics giving two edges of your triangle is linear. Then the convexity is the weakest one. And what is known is such triangle is flat. And triangle is flat means that the convex half of three edges is isometric to Euclidean one. Okay. And in the proof of our main theorem, what I mean by this line is what I told you, what I have told you. So if the distance function has the weakest convexity in some sense, then we can expect that the set is flat. But this is not a concrete mathematical statement. But it is sometimes true. And in the proof of our theorem, proof of our main theorem, we use another version of this kind of assertion. And there, the weakest convexity is different from this. It's not a straightforward one. And I will explain you it later. Okay. Let me briefly remind you the definition of the boundary of cat0 space. It's already appeared in Anders' talk, but let me give a definition. And so geodesic defined on half infinite interval is called geodesic ray. And two geodesic rays are asymptotic if they stay in a bounded distance. And this relation is, it becomes equivalence relation, and you can think of the quotient of the geodesic set of geodesic rays by this relation. And this is the boundary infinity of y as a set. So this is just a definition as a set, but you can attach this set to y by regarding each asymptotic class to be the position at time infinity of geodesic rays belonging here, belonging to it. And so, for example, if y is Euclidean space, then two geodesic rays are asymptotic if and only if they are parallel in usual sense. And so this boundary at infinity of Rn can be identified with a set of all directions. And it's n-1 sphere. And if you take y to be hyperbolic space, then so this is the Poincaré-Ball model of hyperbolic space. And in this model, two geodesic rays are asymptotic if and only if it touches the same point of the sphere bounding this open unit ball. And so, so boundary at infinity of hyperbolic space can be identified with this sphere bounding open unit ball. And this picture, in this picture, so the way of attaching this boundary to y is nicely expressed. Just, yeah. And if y is a Riemannian manifold, then the boundary at infinity is always homeomorphic to sphere. But if y is not manifold, then boundary can be a complicated space. For example, y is 3, then boundary is a countable set. And let me make some remark. Every isometry of y extends to homeomorphism of boundary at infinity, because isometry maps sends the geodesic rays to geodesic rays, and of course it preserves the distance. So this induces a map on the asymptotic classes, set of asymptotic classes, and actually it becomes a homeomorphism of the boundary. And also, if y is locally compact, then so this union, y and its boundary becomes compact. I will use this later. Okay. So now, let us turn to random walk. So let gamma be a countable group with the probability measure mu. And we assume that mu is symmetric and irreducible. And I already explained this, but let me remind you. So mu is symmetric if it takes the same value at gamma and its inverse. And irreducible means that the support of this measure mu generates gamma. And so this mu generates a random walk on gamma in the following way. So let omega p, this is a probability space, as the half infinite product of the pair gamma mu. And so p is the product measure. And so, and at each factor, you make a choice according to the probability given by mu. So at the first factor, you choose some element of gamma. Then it is your position at time 1. And at the second factor, you make another choice. Then you multiply your choice to the position at time 1, your position at time 1 from the right. And so repeated this. Then this gives the work on gamma. So take any element, small omega, from this set. It's just a sequence of element of gamma. And so, as I told you, this gives the work on gamma, and the position of this work at time n is given by this. So product of omega 1 up to omega n. And I denote the map assigns omega to its position of time n by gamma n. And let's consider measure obtained as the push forward of P by this map gamma n. Then, so because P is given as the product measure, and this map gamma n only deals with the your choice up to time n. So you get the product of n probabilities here. And so this gives the probability of reaching gamma at time n through the path given by increments omega 1 up to omega n. And there are other paths brings you to gamma at time n. So we should sum up all of them. So this is just a definition of this. And this gives you the probability of reaching gamma at time n. And so looking at this, you see that this is just the nth convolution of mu, measure mu. So I denote it by mu n. Okay. And so we define mu n, and this set, this probability space gamma mu n describes the distribution of the position at time n. And Poisson boundary of gamma is something like the limit of this. So letting n infinity here doesn't make any sense. But there is a way to define this correctly. And so and that space must describe the distribution of the position of random walk at time infinity. And if the random walk diverges, which means that almost all walk leaves finite, every finite set eventually, then this space can be viewed as the boundary of at infinity of gamma. And there's a natural action of gamma on this space. So is this okay so far? And now, so let this group gamma acts on space cat 0 space y. And we are going to transplant the random walk on gamma to y via orbit map. And looking at the behavior of that random walk. Okay, so gamma is a countable group with a probability measure as before, and YB a cat zero space. And so mu has finite case moment. Here I give you the definition of moment. And finite case moment with respect to the action rho, if this integral is finite. And this integral is the case power of the distance between p, and so p moved by the action of gamma. And this integral depends on p, of course, but being finite is independent of p. So it's because of triangle inequality and some integral inequality. Yes, k is positive. And basically, I only deal with 1 and 2. Okay. And if mu has finite first moment, so then by so-called Kingman's subadditive ergodic theorem, we see that the function assigning omega to this function, this value, so this is a function on omega, converges to a constant function. So here, the distance between, we transplant the random walk via orbit map. So this P is the start point of the transplanted random walk. And here is a position at time n. And so this is the distance between the start point and position at time n, and divided by n. So, but according to this Kingman's subadditive ergodic theorem, this converges to a constant function in L1, omega p. And this constant is called rate of escape of rho of gamma. And so this measures the speed of the random walk leaving from the start point and going to infinity. So if this is positive, then the random walk leaves every bounded set so fast. And so here is a very important and beautiful theorem due to Anders and Margulis. And if I denote this rate of escape by L sub rho of gamma, if this rate of escape is positive, then for almost all omega, so this walk starting from P converges to a point at infinity. More precisely speaking, so this theorem says if this is positive, then for almost every omega, so there is a geodesic ray starting from P, and this trajectory cannot be so far away from this geodesic ray. And it converges to the point at infinity defined by this geodesic ray. And so this theorem gives the map from the position at time infinity of almost every omega to the point at infinity of y. And this induces a map from Poisson boundary to boundary of y. So this is our canonical boundary map. And when I read this paper, so I thought this case, this positive rate of escape case, is a kind of rare case, because here almost every random walk goes almost straight along the geodesic. And because it's random walk, so it should be more wandering, I thought. And so I thought this case is rare. But I was wrong. And the fact is that this case is generic. And so this follows from the main theorem of this talk. And so this theorem says if the rate of escape is 0, then we can completely determine its action under certain assumption. And Y is either locally compact or telescopic dimension finite. So I assume this for Y. And so this is assumption on mu, but the same as before. Mu has finite second moment with respect to rho. And the assumption on the action is here. Rho of gamma does not fix a point in boundary at infinity. Then, so there is a convex subset isometric to Euclidean space, which is invariant under the action of gamma. So this only happens, there is an invariant flat subspace. So in that case, in that sense, this case should be generic. Okay. So then combining these two theorems, so we can prove that theorem I show you at the beginning of this talk. So under the same assumption, so we have two possibilities. There is an invariant flat subspace, or there is a canonical equivariant boundary map. And this case, first case, corresponds to the case that the rate of escape is equal to 0. And second case corresponds to the case that rate of escape is positive. So the situation is very simple. Okay. So let me explain some idea of the proof of our main theorem. And in the proof, I use the rho equivariant harmonic map from group gamma into the cat zero space Y. And rho equivariance is the same as I told you before. It's compatible with the action on the both space. And here, the action of the gamma on itself is given by the multiplication from the left. So left action. And so we consider the rho equivariant map from gamma to Y. So because of this equivariance, this map is completely determined by the image of identity element. So f of gamma is equal to rho of gamma f of E. And so equivariant map, rho equivariant map is harmonic if f minimizes the energy among all rho equivariant maps. And energy is defined in this formula. And this is just the second moment, taking the P as the f of V. So our assumption on mu our assumption on mu about the finite second moment is for energy to make sense. And if rho of gamma does not fix a point in the boundary, then there is a rho equivariant harmonic map. So existence is guaranteed by this assumption. And so although the space Y is a metric space, but so first variation formula makes sense, and it shows that f is harmonic if and only if the image of the identity element is barycenter of f star mu. So the push forward of mu by f. And so by our definition of random walk, the support of mu is just the neighbors of the identity element. What I mean is that the elements belonging to the support of mu is the elements that we can reach in one step. So it's neighbors. Then, so this says simply that so image of identity element must be located at the barycenter of the neighbors, image of neighbors. And so if you say in this way, so this is true for any gamma. So every element gamma in this group gamma, so its image is located at the barycenter of the image of its neighbors. And then, and I use so this harmonic map to prove our main theorem. And it goes like this. So harmonic map have this this interesting but easy property. So assume that f is harmonic and take any convex function on y. Then the Laplacian of pullback of this function u by harmonic map f is subharmonic. So the value of Laplacian is non-positive. And here, Laplacian of function on gamma is defined to be this one. So it's the difference of the value at gamma and the average of the values on its neighbors. Okay. But this is very easy to see because f is harmonic, so assume that the image of neighbors of a given element is the fingertips. Then, so this element must be sent by this harmonic map to its barycenter. It's somewhere around here. And convex function behaves like this. So the average over neighbors cannot be less than the value at its barycenter. So this means, this just proves this. And so doing like this, you see that this value measures the strength of the convexity of U around your point. So if convexity is strong, convexity of U is strong, then it behaves like this. And so this must be very negative. On the other hand, if this is equal to 0, then it means the convexity of this function U is the weakest possible one around that point, around the image of that point. So please keep this in mind. So this is the point. Okay. So let's take distance function from the image of identity element. So this is convex function on y. And pull back this function by f. And let this denote by h. And take the Laplacian of this function. Then it can be written like this. So here is the value at gamma. And this is the average over its neighbors. And because we are taking the harmonic map, so this is subharmonic and it is non-positive. So now integrate this function with respect to measure mu n. Then, so let's see what happens. Okay, so the first term is easy. Just this is so integrate this by this measure. And so recalling the definition of this mu n, we can rewrite this first term in this way. So it's mu n is a push forward of P by the map gamma n. We can write in this way. And about the second term, so it's better to move this measure here. And you see that this integral is with respect to the convolution of mu n and mu. And it's mu n plus 1. In the same way, you can write in this way. So there's a difference between time at n and at time n plus 1. And so remember that so if you divide this by n and let n go to infinity, then you get the rate of escape. So if this difference is uniform in n, then so you get the positive rate of escape. Okay. So if this difference is uniform in n, then dividing this by n and letting n go to infinity gives you the positive value, because each time, so this increases by a certain amount. So dividing n and letting n go to infinity gives you a positive. And okay, oh, I'm sorry. And here, so this is just the difference of two integrals. But going back to here, then so you see that this is a single integral, and integrand here is non-positive. So, okay, and now we assume that rate of escape is 0. Then, so roughly speaking, this difference tends to 0. And so here, the same quantity is expressed as the integral of a non-positive function. So this says that so letting n goes to infinity, then this function tends to 0. This almost everywhere. But so we have to be careful, because so here the function is fixed, but the measure is moving. So we have to fix it. But it's easy. Just rewrite this expression using the definition of mu n. And this is here. So mu n is a push forward of P by map gamma n. So we can rewrite in this way. Then, so you see that so now the measure is fixed, and here is the function of omega. And this is just the so same as this one. It is Laplacian, but we are taking Laplacian at position at time n. And because this integral tends to 0 as n goes to infinity, and integrand is non-positive, so this integrand tends to 0, at least almost everywhere. So what we get from this is this. So if L rho of gamma, rate of escape is equal to 0, then for almost all omega, so this goes to 0. This is just this integrand. And here, so H is the pullback of distance function with base point f of v. So, but this is not so convenient, because the point we are taking, Laplacian is moving. And we want to fix this point, but it's easy. Just move this by isometry, because so these are distance functions. So just apply gamma n of omega inverse to all these elements here. Then you get the distance function with base point f of gamma n of omega inverse. And the point we are taking Laplacian is replaced by the identity element. So just apply gamma n over omega inverse to these elements. Now, so the point taking the Laplacian is fixed, but the function is moving. So base point is moving. So now just take the limit of this. Then because y is locally compact, you can find the limit of this sequence by passing to a subsequence. And so you get a limit function. And if this limit is in y, then this function converges to a distance function from xi. And this xi, if this xi is in the boundary at infinity, then this diverges. So we have to normalize this, but it's done by subtracting the distance between this base point and some fixed point, say f of e. Then what you get is Boltzmann function. So already explained in Anders' book. And so what we get at the limit is, in any case, so distance-like function, and it both are convex. And because we're taking limit of this sequence, so the pullback of this distance-like function by harmonic map F has the Laplacian 0 at identity element. And with little more effort, so we can show that this pullback of U is harmonic on whole gamma. So Laplacian vanishes on whole gamma. And as I told you, if the pullback of convex function has 0 Laplacian, then it means that function has the weakest possible convexity around the image of the point. So we conclude that U has the weakest possible convexity around the image of harmonic map F. And now I hope you can believe that the convex hull of image of F can be flat. But it's not straightforward because this asset f of gamma is very small. So this is just the orbit of the action of gamma, countable group gamma. So typically it's nowhere dense in the convex hull of it. And for example, it can be discrete. So it has a huge complement. And we have to fill that complement to conclude that the convex hull of f of gamma is flat. But it's possible by using this weakest possible convexity or tenth convexity of distance function. Okay. And that gives the proof of our main theorem. Okay, I think it's better to stop here. Thank you for your attention.